welcome to this lecture where we will actually begin our study on geometry of surfaces as we did for geometry of curves. Now, how do you get the feeling of a geometry for a surface S? So, as we know, it consists of a surface will be consisting of different surface patches. So, this be one surface patch. Where is my U? This is my surface S. Now, to get the feeling of a geometry, intuitively what you understand? If you want to have the feeling of a terrain, what you do? You walk on the terrain. So, similarly for surfaces, what you do? You try to take a curve gamma t, which is on the surface. So, it will be of the form sigma u t v t. Supposing the surface patch we are looking at sigma u v, and we try to measure different quantities or try relate quantities to surface along the curve. So, first thing we know about a curve, that so let us come here. So, I have gamma t is equal to sigma u t v t is part of a curve. I do not need part of a curve or the full curve, part of a curve on sigma u, right. This is our one surface patch we are looking at. Now, T must belongs to some alpha beta, and starting at T naught, length of gamma is up to a point T is given by, we know from our discussion on curves, gamma dot T dt. I should not be using T in this variable, maybe I put x. Okay. Well, now what is this quantity? Just have a look at gamma dot at x. This is gamma t is this fellow. So, this will be sigma u dot plus sigma v dot, where u dot denotes du dx, right, and v dot is, so I am applying chain rule here. So, what is this quantity? The norm of gamma dot. Norm of a vector I can calculate if I take inner product with itself. So, that is sigma u dot sigma v dot inner product with itself, correct. Let us expand this. What will happen? You do the multiplication, that will be sigma u dot sigma u, that will give you sigma norm of sigma u square, then u dot square, cos term will come twice, sigma v u dot v dot plus sigma v square v dot square. Okay. Let us call this quantity E. This is dependent on u, this quantity f, and this as g. So, this is going to be important. So, I write it again for the surface patch. What is our denotation? It is a very standard notation. E is sigma u norm square, f is sigma u dot sigma v, and g is sigma v square. Remember this, huh? So, corresponding to the surface patch sigma, I define this quantity E, F and G. This depends on the surface patch. On the same surface, if you have two patches, this E, F and G will change. So, this fellow I can write it as E u dot square 2 F u dot v dot plus G v dot square. Now, so S becomes, so S t becomes T naught to T E u dot square 2 F u dot v dot plus G. So, I am writing the same thing G v dot square power half. So, this, oh sorry, this was norm square, right? Okay. So, I have to put a square root here. Now, if I put du dx, this was u dot square dx square, this is du square only. So, this is just notation. What I get is next page S t equal to T naught to T E du square 2 F du dv plus G dv square power half d, correct. The usual form we write this. So, this is just a notation d square is equal to E du square 2 F du dv plus G dv square. This fellow is known as first fundamental form F, this is the abbreviation we will follow throughout, of the surface patch sigma. First fundamental form, okay, the first time we are assuming, the first time we are seeing such an expression. So, therefore, first fundamental, it is really fundamental in the sense that if I integrate this square root of the first fundamental form, then what I get? I get the length of the curve. And why form? Form, well, form I am not defining what is a form explicitly, but any form what it does is that it acts on a curve. For instance, here it acts on the curve gamma to give a real number. In this case, first fundamental form gives length of the curve. So, clear? Always remember this expression, this is first fundamental form. Soon we will see a second fundamental form. These two are very important, as we see today itself. Now, you will see immediately that what we have decided, that we will, whatever property you want to surface you want to define, it has to be up to reparameterization. So, if I have a reparameterization of sigma, let us say sigma tilde, so that is sigma tilde u tilde v tilde, then you look at the Jacobian matrix of del old by del new, right, del u du du tilde dv du tilde du dv tilde dv dv tilde. You will see that first fundamental form, if I write f in the matrix form, E f f, this is the usual way of writing, just shorter way of writing the first fundamental form. Okay. This is usually denoted by f1. Then this matrix and reparameterized matrix will have this relation. So, first fundamental form is up to this Jacobian change of the Jacobian matrix reparametrization, if I do reparametrization. So, what are the things that remain same under first fundamental form? Of course, length of a curve. Why? Because in the length of a curve, that is from the derivation itself, we have seen that actually the first fundamental form well integrated gives you length of the curve, and length of a curve does not depend on reparametrization. So, that will remain unchanged. If I translate my surface, translation will give the Jacobian matrix identity. So, that will give the first fundamental form is preserved under translation. So, we are going to use that and see an example. So, let us say example 1. Let us take the previous example. Sigma u v is 1 minus V p plus V gamma u. This was generalized cone, right. So, you have a curve gamma out here, you have a point, it is a rule surface, and lines passing through P, and okay, this is gamma. So, that gives a surface, you have to remove the point P. So, actually this is your surface and it has a opposite one. If I take the image of gamma with respect to P, I will have this one. So, let us consider the upper part only without P. So, this is my surface. Okay, now as I said, I can take P to be 0. Why? Translate by P. So, you get new parametrization, which will give you, if you simplify, V into gamma u minus P. So, replace now, translate the curve also, gamma by gamma 1, which is the translation of the curve gamma. So, I get, so we can have sigma 1 u v is actually V into gamma 1 u. So, now surface this P is 0, P is origin now after translation, right. And I must know gamma must not pass through P, I know what. So, we put the regularity condition. Regularity condition, last time we saw that gamma does not pass through the origin, and gamma is smooth curve, of course. I take this gamma to be smooth. To get the surface, a regular smooth surface. Okay. Now, let us make gamma tilde u, let us make one more change, just so that this instead of gamma I consider gamma tilde, but I make the change u tilde equal to u and v tilde equal to v by gamma u. So, change of variable. Then I will get my surface which is a nice form, u tilde v tilde equal to v tilde gamma tilde u tilde, but in this case I have gamma tilde u tilde, this is always norm 1 because of this, right. Okay. Now, I do another parameterization. So, I am making things easier to calculate, reparameterization, so that gamma tilde is unit speed, that we know how to do it, we just have to change u tilde to something. So, we assume gamma tilde is unit speed. Now, what happens to the first fundamental form? So, what is gamma u tilde? So, finally, let us take the surface to be sigma u v equal to v gamma u, where gamma u norm 1, gamma dot u norm 1, after reparameterization I get this one. So, this page what I did all these things is reparameterize the cone in such a way that my surface looks like this. So, now it is very easy. What is sigma u? Sigma u is just your V remains same, gamma dot u, and what is sigma v? Sigma v is gamma u. So, E equal to, and okay, what is sigma u v? Sigma u, okay, let us calculate sigma u square, this is v square norm of gamma dot u square, but we have assumed unit speed, so v square. Gamma v square, this is simply gamma u square, so this is again 1. Okay. And sigma u dot sigma v, this is v into gamma u dot u, but gamma u and gamma dot u, this inner product is 0. Why? Because gamma u square is 1, if you differentiate 2 gamma u, gamma dot u is 0. So, that gives this, the cross term is 0. So, f is 0, this is g. So, first fundamental form for the cone becomes v square du square plus dv square. Let us go to another example. Let us take the plane. Where P is perpendicular to Q, unit vectors. We have done this example, if you recall the last lecture. Here it is very easy to calculate. You can see FFF will be just, you calculate, or sigma u is just P, sigma v is Q, but both are unit vectors, so norm 1. So, it will be du square dv square. Okay. Let us take the generalized cylinder. Or the cylinder itself, the most fun, this is gamma u plus V x. Let us take, and x is a unit vector. And gamma is unit speed. That is gamma dot u square equal to 1. If you calculate the FFF here, you will get, this is again du square dv square. So, plane and cylinder has, they both have same fundamental form, it signifies something geometrically, and I will try to recall you that what we did in one of the examples. Suppose I take the standard cylinder here, cylinders of radius 1, correct. So, gamma is your curve cos u sin u, and the cylinder is cos u sin u v, right. And then you look at the yz plane, this plane of length 2 pi. Then we have done this thing before, that I can wrap the plane into the cylinder. So, recall this wrapping a plane onto a cylinder. And this map, this wrapping map, this is very interesting map. This what happens that if I have a curve on the plane, that will be wrapped and moved to some curve on the plane, but their length will be preserved. So, what it says that this wrapping map, whatever it is, we have done it before, that is actually a isometry. So, here in this particular case, the isometry is, this is the cylinder, this is YZ plane. So, this is an isometry. What is isometry? That preserves the length of curves. Since this is an isometry, they have first fundamental form same, and that it was the theorem I want to prove, then everything will become clear to you now. Okay. So, let's like a definition. I have two surfaces and f from S1 to S2 a diffeomorphism. I am talking about regular smooth surfaces. So, I should take diffeomorphism. F is called an isometry if for each curve gamma on S1 length of gamma equal to length of f gamma. So, f will take this curve to gamma to another curve f gamma. They must have, if they have same length, this is called isometry, and obviously the theorem we are looking for is what I was trying to explain through this wrapping the plane, that for it is true in general that if S1 f from S1 to S2, this is isometry if and only if for any surface patch sigma 1 on S1, sigma 1 and f compose sigma 1, this is a surface patch I know, this is a surface patch, this is a surface patch on S2. So, sigma 1 and f sigma 1 have same first fundamental form, and that is exactly what is happening in the case of plane and generalized cylinder, because this is an isometry and they have the same fundamental form. In this case, both are single patch. Okay. Okay. So, let us quickly try to see the proof. First part, suppose FFF of sigma 1 is same as FFF of f sigma 1. Then you will see immediately that after all, if I take a curve, then ds square is FFF is given by the first fundamental form, and since fundamental forms are same, this ds square element is same. So, length of the curve will be preserved. So, length of curves are preserved, hence f is isometry. So, this part is really straightforward. Okay. Now, the other way is little non-trivial, it is not really non-trivial, I mean you have to do little bit of work. So, conversely, let f is an isometry. What I have to show? The surface patches for sigma 1 and sigma 2 are same, sorry, sigma 1 and sigma 2, to show sigma 1 and f compose sigma 1 has same FFF. Well, the FFF of sigma 1 we will denote by E1 F1 G1 here with E2 F2 G2. Since isometry, then what I have for all T naught T1, length is preserved. Okay. But this relation is true, this integral equation is true for all T naught and T1, whatever curve you take. That will imply these two are same. Here I should have written u tilde actually, okay, u dot square plus 2 f dot u dot v dot g dot v dot square. But what I have to show? I have to show E1 equal to E2, F1 equal to F2, G1 equal to G2. This does not give the first fundamental forms are same. Since they are same, now I take special case. Take curve, consider this curve u equal to u naught plus t minus t naught. If you do it, you will see this terms will vanish and that will give you E1 equal to E2. Similarly, and v equal to v naught. Similarly, take u equal to u naught and v equal to v naught starting at some u naught v naught at some fixed point, that will give you G1 equal to G2. Now, put them back or to consider this curve u naught t minus t naught and v equal to v naught plus t minus t naught, this curve, since this will implies 1 plus 2 and along with 3 will give you F1 equal to F2. Okay, so, this is the more or less sketch of the proof. This book proof is available in any book, in particular whatever the references I have given you can check that. That is it for today. Next time we will see another kind of map, conformal maps.